So today we're going to talk a little bit about how computers store and represent both positive and negative numbers. This is a little tricky in that it's not as straightforward as an unsigned system. We have to deal with the fact that we have to split up our number space so that it can accommodate both positive and negative values. And there's no set way to do this. There are some very well-defined and well-accepted ways to do this, however, and those are the ways we're going to talk about today. I'm going to talk about a couple of ways first that are not so commonly used, and then we're going to talk in relative detail about 2's complement representation, which is probably the most commonly used way to store both positive and negative numbers. So let's get started. Okay, so what we're going to start with is a table here with binary representation and decimal representation of our integer values. And a couple of things to note about the system that we're going to be using. The system that I'm going to use for these particular examples is a 3-bit system. Now let's quickly review. Anytime you have n bits, you always can represent 2 to the n possible values. So we have a 3-bit system. 2 to the third is equal to 8, hence our 0 through 7 possible values. And so we have our binary 3-bit system and our decimal representations here as well. I use 3 bits just to keep it simple and small. Every time you add a bit, you double the possible number of values. So with a 4-bit system, we'd have 16 possible values, and that could get tedious. So we'll keep it simple with 3 bits, and we can illustrate all of the concepts that we need to with this particular tip. So again, this is an unsigned system, i.e. we have 8 possible binary values, and we have 8 decimal values, all of which are unsigned, positive values. Not real interesting for what we're trying to do. We want to have a system where we can split up this binary number space so that we have some of the numbers positive and some of the numbers negative. Ideally, we'd like half and half positive, half negative. But let's just see how we can do this. I'm going to erase these values here because that's just one way to interpret these binary representations. If we want to deal with signed values, in other words, some signed and some not, some positive and some not, we have to split these up into a set of positive and negative values. Let's look at the first method. The first one that I'm going to talk about is called sign and magnitude. And the way this works is we simply divide our number space in half. Half the numbers are positive and half are negative, and the positive numbers are represented by a leading 0. The negative numbers all are represented by a leading 1. And so our representations would look like this. 0, 1, 2, and 3. That takes up all of our positive values. And then we simply use the rest for the negative representations. Negative 0, negative 1, negative 2, and negative 3. So this is a simple sign and magnitude system. Our sign is a first bit. If it's a 0, it's positive. If it's a 1, it's negative. And then the remaining bits represent the magnitude of the number. Now, this has some drawbacks, one of which is the idea of 2 zeros. A negative 0, 2 zeros doesn't make a lot of intuitive sense, but a negative 0 makes even less intuitive sense. And so that's sort of an ugly artifact of sign and magnitude. And we're going to see that at least one more of our systems have the same artifact. That's not really a good thing. There's some other problems too with this that cause it to present some problems when we implement this in hardware. And I'm not going to get into the details of the hardware issues that go along with how we represent negative numbers. But suffice it to say that sign and magnitude has the 2 zeros problem, plus it's difficult to implement in hardware. Let's look at the second mechanism. So that's not an ideal way to do it. At least for our purposes, it's not an ideal way to do it. Another way we can represent negative numbers is with what's called 1's complement. And all 1's complement really amounts to is if we have an original, let's see, there we go, an original value, to get the negative of the original, we simply flip the bits. It's a very straightforward process. So let's just say, for argument's sake, I have we got our 0 and our 1 here. With 1's complement, if I want to get the negative of 1, well, the positive of 1 is 0, 0, 1. The negative would be, well, I'd simply flip the bits, 1, 1, 0. So this would be our positive 1. This would be our negative 1. Okay, and so 1, 1, 0 is right here. That would be our negative 1. So if this is a 2, 0, 1, 0, we can flip the bits to get the negative 2. 1, 0, 1. 1, 0, 1 would be our negative 2. 3 right here, negative, so that is 0, 1, 1, and to flip those bits would be 1, 0, 0, so this would be our negative 3. Notice we still have this 0, and so let's do the 0 real quick, give myself a little bit of room. I've got a 0 represented as 0, 0, 0. To flip those bits makes it a 1, 1, 1, and again we get a negative 0. Not intuitive, kind of ugly, but it's another way to represent negative numbers. And again, this is going to have some implementation issues in hardware. We're going to solve both of these problems, however, with the notion of 2's complement. 2's complement is really nice in that it solves these problems. So let's take a look at it. With 2's complement, we have an original value, and to get the negative, we do a couple of things. Just like with 1's complement, we flip the bits first. We have another step then. Once we flip the bits, we add 1. That's it. That's all there is to 2's complement. If I have an original value, if I want the negative of that value, I simply flip the bits and then I add 1 to it. And that would be my negative representation. Let's see how this might play out. I'll put this back up. Okay, so if I have a 0, now we've had the problem with 2 zeros up to this point. Let's see if we still have the same problem. If I have a 0 and I want the negative of that, I would, well, 0 is represented as 0, 0, 0. If I'm taking the 2's complement negative value, I would flip the bits, so that gives me a 1, 1, 1, and then add 1. If I add 1 to this, 1 plus 1 is 1, 0. 1 plus 1 is 1, 0. 1 plus 1 is 1, 0. Now what's interesting about this result is it's a 4-bit number. We have a 3-bit system, so this number is not even supported. In fact, it's a carry bit right there, and we can simply ignore it, which leaves us with 0, 0, 0, or the same value we started with. So there is no notion of a negative 0. 2's complement works very nicely to solve the 2 zeros problem.